Now we introduce the guided policy search for robots and unknown dynamics. First, we introduce the basic problem. This P is a controller. We use this controller to generate demonstration trajectory. This pi is a policy, which we will learn by using reinforcement learning method. And this OT is an input, is a observation, is a RGB image from a robot camera. Right now, in this case, we suppose the dynamics P is unknown. So this is like a model-free system or dynamic. We still use expectation loss to as the objective function to measure the loss along the trajectory tau and policy pi. So the problem is expressed as the constraint minimum problem. Once we make this expectation loss minimum and subject to this policy same as the controller. So this constraint leads to the supervised policy learning problem, while the minimum formulation we can get reform as a trajectory optimization problem. Let's go to the detail. Let's say we have a system. We use this controller operate on the system, real system. It's from state S. Then we take action, select the action A prime. We suppose we go this next state. However, because of the dynamic environment, the final actual point is next state is here. So they have a difference. Because it's unknown dynamics, so we need to use this difference to step by step improve our controller, make sure this two states close each other. Once we get this controller, then this controller uses as the target to train our policy. That means we use a large amount of training data. See, in a different dynamic environment, how can we select action to generate a correct or optimal trajectory and reach the correct destination point. Since then, the controller and the policy even we know, but we don't know the system dynamic, so we cannot directly compare the trajectories generated by the policy and the controller. So we have to use different methods to solve this problem. So based on the backup diagram, for example, start from this state S, we run a real robot, use this controller. However, we don't know the system dynamic. We plan to reach S prime. However, due to the influence of dynamic environment, we reach this point. That means we observe this, the actual position. So they have a difference. They have a difference because we don't know the system dynamic. So we use this difference to step by step improve the controller, make sure finally, these 2 points or 2 states are very close to each other. Once we get this controller, then we use this controller as a target to train the policy. Train the policy by means use large amount of training data. Make sure at the same situation, policy model can select the correct policy or select the correct action to generate a correct or optimal trajectory, reach the correct destination point. Of course, this, we in a high dimensional action space. So how can we select this action? So we use the policy network. Policy network means we give a network, RGB image as an input and see what's the optimal action for the policy. And of course, we use this controller as the target. This controller, of course, is step by step improved by the two trajectories. One is the observed trajectory. One other is that we operate the controller on the physical system, generate the trajectory. This along the trajectory tau, the loss is used to improve the controller. That's a basic idea. So solve the problem, we split the problem into two parts. First, of course, this trajectory optimization. That means we suppose the dynamic and the controller Gaussian distribution, so we can write the controller and the dynamic in the Gaussian distribution, and then we get an objective function to solve them to get correct controller. Once we get a correct controller, use it as a target to train the policy. We again assume policy and the controller Gaussian distributions, so we get an objective function by using their mean and the covariance, make sure they are close to each other and generate the optimal trajectory, and finally get the final correct destination point. So for more information, you can check these articles. Thank you.